Tonight, let's get to talk to us about a pretty cool thing, smart buildings. And I don't think I see it. I think we're going to have a special guest because the question is, are smart buildings smarter than Alexa? And we're not talking about an infinity here, we're talking about Alexa. Did that joke work last time? No. Okay. So, please join me in welcoming Raj Gopal to Wednesday Night Live.
Good evening, ladies and gentlemen. Can you hear me?
Yes.
I want to first thank Tom for the nice introduction. And I consider it an honor and privilege to be standing here and give my talk at this prestigious Wednesday night at the lab. Today I'm going to talk about smart buildings. Are they smarter than Alexa? The presentation outline is smart building and smart building HVAC system definition. If you look at the literature, there are not appropriate definitions for these two. So I have decided to give my definition, the way I view it, and you will shortly see that. And I'm going to provide some background information which will justify why we need to look at demand response and automatic fault detection and diagnosis. Then I will share with you my experiments with Alexa and with smart outlets using Smart Hub. I used it mainly from the perspective of energy analysis consumption. Now, when you look at the skyline, what comes to your mind? There are a lot of large buildings, office buildings, they consume a lot of energy. And there does potential exist for saving energy. Not only that, should any fault occur in any of these buildings, which may be 50 floors or 100 floors, it's very difficult for a maintenance crew to find out where the fault is, how to rectify it, how to restore the system. And faults are killers of energy savings. So we have to deal with two issues. From the electric utility point of view, they want to provide reliable power at all times. So if the peak demand is high, it sort of creates problems for the electric utility to maintain generation to match the demand. You have seen these ads before. What comes to your mind when you look at this ad? Reliability. Reliability is a very important criteria in terms of building comfort situations, building environmental quality, and if you look at utility in terms of reliable supply of electricity to end users. Now, this is my definition of what a smart building architecture should look like. This is the gateway of the smart building architecture, which I call it as the smart building facility management system. Then you have got several subsystems: smart building HVAC, smart building security system, smart building access system, and smart building life safety system. My focus today is going to be on smart building HVAC system. Now, each subsystem is an autonomous, intelligent, self-healing, resilient system. This architecture does not exist today. The architecture exists today, they do to some extent the different subsystems, but not in a fashion of intelligent, autonomous, self-healing systems. Another important thing that I introduce, if you look at it, is the smart building teacher. What it does is, if this smart building facility management system has been installed by the company in several buildings, it collects the data from all the buildings and stores in it, such as performance, such as energy savings, such as energy cost savings, the control loop performance. Everything is residing in this smart building teacher. Now, if you take smart building HVAC system, when I say a system is resilient and a system is self-healing, if you take a cooling coil, if you have the valve in the cooling coil supplying chilled water to the cooling coil, say the valve, instead of going to the full open position, gets stuck at 50%. If it's a resilient system having end-to-end resiliency, it will send a signal to the chilled water supply from the chiller to reduce the temperature of the chilled water so the capacity of the cooling coil can be increased. So this is an example of resiliency and self-healing. Now, another thing to consider is the smart energy resource center controller. This comes into play when the building has got renewable energy such as photovoltaics or backup power generation or energy discharge from electric vehicles. So this one optimally controls the resources that may come into play from the building. Now, this smart building facility management system, once it gets all the information, sends it to the dashboard here for the operator to look at, and this can be sent to smartphones, tablets, or computer, or TV, or smartwatch, whatever you have. Now, this is my definition of what a smart building HVAC system should be. A smart building HVAC system is a self-healing and resilient autonomous intelligent system maintaining thermal comfort and indoor environmental quality at desired levels for occupants with minimum energy use. Today I am going to talk, the first section I am going to talk is about demand response to real-time pricing. How do you respond when the electric utility sends you a signal for real-time pricing? And this paper I presented last year in Denmark at the 12th World Congress of the European Heating and Air Conditioning Association. Now, this is very interesting. This is the interesting data from the Energy Information Administration, EIA, for the United States 2012 survey for commercial building energy consumption survey, that's called CBETS. If you notice in this, large office buildings greater than 100,000 square feet, though they consume only 2% of all building stock, they are responsible for 35% of all floor area. And they consume 30 kilowatt hours per square foot per area of energy. That roughly works out to be about 100,000 BTU per square foot per year. And there are 24,000 buildings like this, and the total annual energy consumption of all these buildings is 180 billion kilowatt hours. And the median operating hours is 47 hours, which is important. That shows there are occupied periods and unoccupied periods, which is very important for us when I talk about fault detection and diagnosis, or when I talk about demand response. The median age of all these buildings is 33 years. Now these are, as I said, are ideal candidates for real-time pricing, RTP, and automatic fault detection and diagnosis, AFDD. Now, what are the reasons for demand response program, you may ask? First is to provide a reliable source of power. Second is to match generation with demand and avoid network instability. The last is avoid the need to use expensive standby power generation to meet short-term peak loads. From the electric utility rate schedule point of view, the standard practice has been to use time of day fixed on-peak and off-peak rates with a demand charge for the on-peak period. Other types of demand response programs, there are several flavors offered by different utilities depending upon their load, their type of customer and on. I'm just indicating a few. One is called resource-oriented demand response program with utility incentives. Here, for example, if the customer offers the utility that I will take off 2 megawatts of your load, the utility pays the customer so many dollars per megawatt shifted away from the utility to the customer. Or the utility may pay kilowatt hour energy savings. If they save so many kilowatt hours, they will get so many cents per kilowatt hour. The last one is the day ahead real-time pricing. It's a demand response program where the utility has got a certain RTP profile every day of the year, and the customer responds to favorable RTP rates during certain periods, thereby saving energy, and this depends on the customer enrollment with the utility. So this could result for the customer, depending on what type of a customer he is, potential exists for energy cost savings. Now here is an example of real-time pricing profiles, RTP, for the summer months. Here I assume it's a summer peaking utility. So if you look at it, I have considered the hot months of July, August, the cooler months like May and September. You can see July and August, the peak is high. And in May and September, it's low. May and September is low, and if you look at carefully, this off-peak period, the rates are much lower than on-peak. So if you have the ability to shift some of your loads to off-peak, you save a considerable amount on energy cost. Not only that, if you can shift even some of the loads which are in this zone to a lower cost area even during the on-peak, you can save some energy costs. Now, I have not included the demand charge in this because the demand charge is based on the entire building system load. And in this case, I'm considering just HVAC and lighting. And this type of RTP profile comes every day of the year, and it's available to the customer one day ahead of time, maybe around 4 o'clock the previous day. It is communicated to the smart building facility management system. Now, my interest was, I was wondering, once I saw the RTP profile and the need to program the control strategies, can we do one day ahead of time, even the programming of control strategies, as opposed to doing on the day RTP occurs? So I decided to look at correlation with outdoor air temperature with RTP profile. The bottom red one is the outdoor air temperature for September. The middle one is the RTP profile for a mild day. Again, you can see there is a qualitative correlation between the outdoor air temperature and the RTP profile, indicating to us that there is potential exists to come up with control strategies as a function of outdoor air temperature one day ahead of time. Now, the type of building I'm considering for this analysis has a building with a floor area of more than 100,000 square feet. It has got a variable air volume system where the flow of air to the occupied zones is varied to match the cooling load in the zone or the occupied area. Then I'm considering centrifugal chillers. They could be air cooled or water cooled. And then I'm considering a control strategy called supply air reset, which is nothing but if the air is leaving the cooling coil, just like in your homes, then the discharge temperature can be reset to a higher temperature if none of the occupied zones call for full cooling. So there is not full demand on the cooling coil, you can raise the temperature. So that's called supply air reset. And chilled water reset, if none of the cooling coils in the entire large building, which has got several air handling units with several cooling coils, we are saying maybe there is the opportunity now to raise the leaving chilled water temperature to a higher level. So that means the differential head pressure in the chiller between the evaporator pressure and the condenser pressure is now smaller. That results in energy savings. Now, optimal start followed by floating control. This is nothing but an optimization program which determines what is the best time to start in the morning your chiller and the air handling unit, such that you reach a certain temperature that you want at the beginning of occupancy, which could be 8 o'clock in the morning. So in this case, for the demand response, if the temperature band of comfort is, say, 73 degrees to 78 degrees in the cooling season, the optimal start is started such that, say, the occupancy is at 8 o'clock, the temperature will be at 73. At occupancy, if it is at 73, then you reset the set point of the occupied zone thermostat to 78. So there is a certain floating time you have from 73 to 78, during which you will not use the chiller. That results in chiller savings. Of course, it results in a little bit extra chiller load, because now instead of keeping it at 78, you are using the optimal start to keep at 73. But remember, this energy occurs during off-peak period. So you are paying lower cost in terms of the chiller energy cost. Now, ice storage. All this means is during the off-peak time, when the rates are low, you make ice. And you melt the ice during the on-peak period. When the rates are high, you melt the ice, and there could be partial ice storage system or a full ice storage system. That really depends on the designer's viewpoint. And of course, full storage is normally not used, it's expensive. Optimal stop. This is a program where you shut off the chiller before the end of occupancy. Say 5 o'clock is the end of occupancy. You may want to shut the chiller based on the optimization program, maybe at 4:04 p.m. or 3:30 or 4:30, so that you make use of the flywheel effect of the chiller capacity available in the chiller pipe. So this results in chiller energy savings. The next one is the schedule lighting control, which you can possibly do, take off a bank of lights in the common areas, not the occupied zones, but the common areas, where you can take out a bank of lights, shut them off when there is not much activity in the common areas such as hallways and all, maybe from 9 in the morning to 11 o'clock in the morning, when all the occupants are in their offices working. And the same thing is true in the afternoon, maybe from 2 o'clock till 4 o'clock. Or you can use motion detectors to do that. Last is the backup power system control, where if you have got a diesel power generation, you want to do an optimization study as to what is the cost of generation of diesel power during the peak period, as opposed to the paying the real-time pricing costs. Now here I chose a complicated system because it justifies the need for automatic fault detection diagnosis. And if you remember, it's very difficult for a maintenance crew of 9 or 8 people to go and diagnose where the fault is. So here on the top two, you find this is the supply fan for the cold air, this is for the hot air, and this is the return fan. So the hot air goes here, the cold air go here, this is the cooling coil, this is the heating coil, and this is the variable air volume box I talked about before, supplying cold air to the interior zones. The reason we use only cold air, because the interior zones are not exposed to perimeter weather, outside weather conditions. Whereas the perimeter zones are exposed to the outside weather conditions. So you need a blend of this hot air as well as cold air. That's why this box is called dual duct variable air volume boxes. So you have one cold air line going through, another hot air going through. You have got a damper here which modulates the amount of cold air that goes into the room and the amount of hot air goes in the room. So in the cooling season, this is pretty much shut off, and the cold air comes into the zone. There is a direct digital controller which sets the set point for the flow, and that's how the mixing takes place. Now here are the dampers, one for exhaust, one for outdoor ventilation air, one for return air mixing with the outdoor ventilation air. Now you can see the potential for fault. I have not even included the chiller equipment and the heating equipment. I have not shown the cooling coil valve nor the heating coil valve. So the fault can occur with the damper, with the set point of the ventilation air, with the outdoor air damper, with the fan, with this fan, or with these boxes, or with the temperature sensors which are here and which are here. So you can have numerous fault scenarios. So the reason I took this was it gives an incentive to look at automatic fault detection system. This is called dual fan, dual duct system. Now you can look at other systems and equipment in the ASHRAE handbook, American Society of Heating and Air Conditioning and Refrigeration Engineers. Now here is my methodology, how to come up with control strategies corresponding to outdoor air temperature. So what I have suggested is, during the commissioning process, when the building is built, it goes through several stages. If you look at one stage almost in the end, it's called operational phase with occupancy. So in other words, you are testing the control strategies and all that before the entire commissioning process is complete. So this is what is done. This is the commissioning process. Now in this phase, the customer is not aware of what the RTP pricing is going to be. He is given the RTP pricing only when he enrolls with the utility. So now during the commissioning process, the RTP pricing control strategies are evaluated for electric vehicles if you want to have power supplied back to the grid. Same thing with renewable energy. You have got zone. As I mentioned, you can raise the set point or lower the set point, as I said about optimal start and the floating control. You can have chiller. I talked about chill water reset. I talked about the fan system, that's called the air handling unit, where you can have supply air reset for the cooling coil, or you can control the variable speed fan. And then you got lighting. I talked about lighting scheduling. So then you got weather station, giving the weather data to the smart building facility management system. Then I talked about the smart building teacher, and then there is the cloud. Now what happens here is, every day of the cooling season, you test the control strategies, which the operator can schedule it so that they come on automatic. And the data collected during the on-peak period, say 8 a.m. to 5 p.m., is sent to the cloud. Because during the on-peak period, when you are testing the control strategies, it's not possible to evaluate the data. So during the off-peak period, when there is no occupancy, then you evaluate the data and come up with the information you need. And at this point, the relevant information is sent to the dashboard where the operator can take a look. Now, these data that you have collected can be represented in this fashion. You can set up for the outdoor air in 3 degrees centigrade bin intervals or 3 to 5 degrees Fahrenheit at particular temperature intervals for each of the hours during the 24-hour period, and you select what is the RTP interval. Most of the RTP intervals done in this country are 1 hour. But there is a possibility that will go to as low as 15 minutes to closely match generation with demand. Then we have what type of a control strategy it is. Is it supply air reset? Is it chilled water reset? Is it floating control? Is it optimal stop? Is it optimal start? So each of those control strategy is evaluated from the commissioning process. And you calculate what is the strategy duration. You cannot leave it on forever. It automatically, it's interconnected. Many of the control strategies are interconnected. So they can last on some days for 15 minutes or half an hour, on some other days for 45 minutes, depending upon the controlled interactions. And so you also identified what is the kilowatt hour reduction. Now the commissioning process I talked about, there are standards for this. This again is through ASHRAE. Now once the commissioning is over, let us assume the customer says, I want to enroll in the RTP program with the electric utility. This is what happens. The customer, post-commissioning, he decides to participate. Then you have the electric utility. It sends a signal, it's called day-ahead RTP, to the smart building facility management system, maybe 4 o'clock the previous day. And this smart building HVAC is the one that executes the control strategies. Remember, I told you before that you can set up the control strategies as a function of outdoor temperature. The weather station here sends the weather data forecast 1 day ahead of time. And again, you have got smart teacher, which I discussed before. So once you have weather data 1 day ahead of time, and from commissioning you have all the control strategies, the smart building facility management system can automatically trigger what control strategy should come at what time. Now the utility, through its smart meter, can determine whether the demand response strategy for that day was successful or not. Maybe at the end of the day, it can look at the kilowatt hour energy consumption or savings and say, yeah, the demand response was successful or it was not successful. If the demand response is successful, as you can see, that input goes to load forecasting by the utility. So the utility can get an idea what is the impact of demand response program. If the answer is no, then that means there is possibly a fault. So automatic fault detection diagnosis, AFDD, is initiated in the smart building HVAC system. And once it determines the fault, the operator can restore the system, or if it's possible to have self-healing and resiliency, it can automatically do it. Now, and the process continues. Now here is I have a weather app on my smartphone, and this is a 24-hour forecasted weather for August 1st for Madison. Now this is from midnight to midnight. Now as you can see here, you make ice. Because this is off-peak time, the rates are low, and if you've got an air-cooled centrifugal chiller, it's a function of outdoor air temperature. The cooler the temperature, more efficient is the centrifugal chiller. So you make ice here, then as you move maybe around 5 o'clock or so, you start the optimal start program based on the decision of the optimization. And around 8 o'clock, I can't see clearly anyway, so around 8 o'clock the occupancy starts, you increase the set point temperature to 78, so there is floating control, and during that time potential exists for supplier reset. Looks like the temperature has not reached the design temperature. So you can do supplier reset during this part, so you're realizing energy savings, and then possibly you introduce lighting control here because people are settled down in their offices and there is potential for lightings to be turned off, a bank of lights in the hallways. And as you proceed further, when the temperature reaches 79 degrees and 80 degrees, maybe the time has come for you to melt the ice. So you will run the chiller as a base chiller, and whatever extra load needs to be met, you melt the ice. So thereby you save on energy and possibly demand. I say possibly because here I'm considering only HVAC load. I really don't know whether the demand is coincident with the entire system load, because the demand is based on the building's entire system load, not just HVAC and lighting. So now, during this, before the end of occupancy, say at 5 o'clock or so, the optimal stop kicks in, providing more energy. The chiller is shut. Around this time, the smart building facility management system gets real-time pricing for the next day. And this process continues every day. Now here is the chiller load profile. The blue line indicates the chiller load before he enrolled in the RTP program, and the red line indicates after enrolling the RTP program. The difference is the energy savings and thereby energy cost savings also. You can see that there is load here because you are making ice in the off-peak period. And also there is a little bit extra energy here because, as I said, optimal start keeps the temperature a little bit towards the lower band so that you can have floating control in the on-peak during the on-peak period. Now here is the same thing as I explained before. The upper portion is chiller load. This is ice is being made. Here is the floating control advantage. Chiller is shut. Then the chiller is run to meet the load. Here, I'm sorry, here is optimal start. Here is the floating control. Here you are melting ice. That's why the peak, it has dropped from here to here. And then here is the optimal stop, which you are shutting about 1 hour or depending on the program early. And here you get the RTP pricing for the next day. And here you make ice and the process continues. At the bottom, these are all energy savings due to different control strategies, which I listed here. Now, I have also introduced a new concept which I call augmented real-time pricing. What is augmented real-time pricing, you may ask me? I have said this real-time pricing is really a charge by the utility to the customer whenever he uses energy. I said, why not a utility pay the customer for sending back kilowatt hours back to the grid? So in this case, for example, the customer may have photovoltaics or other renewable forms of energy or electric vehicles or combined heating and power CHP units. So if he sends back the power, the utility can pay the customer at the RTP rates when they send back the power back to the grid. And this enables better reliability, increases the reliability from generation to demand, and also promotes sustainable energy. Please read the conclusion. Did you guys have a chance to look at the conclusion? Now, this is future work. Obviously, this requires testing in an actual building because whole methodology and the strategies and the idea of outdoor air correlation has not been done before. In fact, I looked at the DOE studies from the Building Energy Technology Division a month ago. They are given a contract to one of the big building automation systems company, and one of the things they are doing is exactly trying to address the issue of trying to develop control strategies to real-time pricing, and the project is model-based control strategy, doing it on the day the real-time pricing occurs using predictive control. I don't know what the success is going to be, but that's a project out there. Now, another problem is the user's cloud. If he decides to go to another cloud, to another vendor, it's difficult to do. Right now, there are not standards for portability of moving data from one cloud to another cloud. Another interesting thing to do is the AFDD, which I will show in the next section. For demand response, the interval is so narrow, if a fault occurs, you may have to have dynamic AFDD, so that the instant you have to constantly monitor it. You need a model, dynamic model, and predictive control. As you move with time, the AFDD should move with time. Anytime it finds a fault, it should diagnose and restore the system. That needs further study. The last is for the utility to directly control the control strategies instead of the smart building facility management doing it. Now this, I'm going to go to AFDD. This is a paper I gave in Prague at the European Heating and Ventilation Air Conditioning Engineers Association's World Congress. And I will now go through what I did. Now, if you look at the left side, where I'm showing the prayer work, the prayer work, they concentrated only on certain component of the entire building. They either looked at just chillers, or they just looked at lighting, or they just looked at air handling unit. They didn't take a global view. Now what I have done is, I have taken a global view. My approach is, another thing, important thing I did was, what drives the fault? If you take the whole building, what drives the fault? I said we should consider 3 primary variables. One is temperature in the occupied zone. One is CO2 level in the occupied zone because of occupants, CO2 generated. We have to keep it at a certain optimal according to the standards. Third is metered energy consumption. I will come to that a little later. Now I'm using, just like before, smart building facility management data, I'm using cloud. Another thing I'm using is energy analysis simulation for the building. Now the energy analysis simulation can tell us what is the optimal supplier reset point, what is the monthly cooling energy consumption, what is the weekly energy consumption by end use, how much for lighting, how much for chillers, how much for fan units, and how much energy for the year. Now, another important thing is we need to have good energy audits specific to AFDD, because AFDD depends on the accuracy of the performance and the characteristics of the components, such as what is the characteristic of the damper, what is the characteristic of the valve. Now I am looking at global fault scenario, just like before I said, I'm looking at the whole system, and if there is a fault, I want to look at all the pieces to see where is the potential for fault. Now another interesting I had in mind, I said about commissioning. Once the commissioning is done, that means you are certifying the building, all the systems and all the components are functionally okay, performance wise they behave all right. So if that is the case, if you have automatic fault detection diagnosis for new buildings, when you take charge of the new buildings, there is no need to do it every minute, every hour or anything. You can probably do it once a week for new buildings. For existing buildings, which are older buildings, probably you need to do every week. For new buildings, every 2 weeks. For existing buildings, every 1 week. Not the control loops. I have to charge myself a little bit. Now, these are the prerequisites which I have stated before. And this is not new, it's the same thing I just said before. Now, this is the process architecture I came up with for my strategy for AFDD. I already talked about smart building HVAC system. I already talked about smart building facility management system. You have the energy meter, which not only gives the whole building energy consumption, it also gives end-use energy consumption. Like what is the energy consumption due to lighting, fans, chillers. Another important thing I forgot to mention, maybe you looked at it. If you take a large office building, the fan energy consumption is 26%. If you take chillers, it's about 17%. If you take lighting, it's about 16%. If you take computers, it's about 17%. And the rest are all miscellaneous loads. The smart teacher already described to you. The only new thing is simulation, which I did go through now. Now the results of the simulation are sent to the smart teacher for validity and comparison of its library of data, and it is sent back to the smart building facility management system. Now, this protocol for HVAC, smart building HVAC system and the smart building facility management system, there are some protocol for the network. You can get this in the ASHRAE standard. Now, the building energy simulation program, there are some programs are listed here, DOE2, Energy Plus. These two are free. They are available from DOE. The last two you have to pay a fee. Trace is from Train Company. And the last one, TRINS, is 18. I don't know whether you are all aware. It's from the UW-Madison Mechanical Engineering Department. And it's available for a fee. And this is for very short time intervals. The others are all taking data every hour. This you can do every second, every minute. You can choose your time interval. Now, what are the measurements that I need? I just listed here. You can even see that. I don't want to repeat it. Now, here is interesting things. What are the fault scenarios that I considered? One is, say space temperature and CO2 are within the range. For example, CO2, they may say it has to be within 1,000 parts per million or 1,200 parts per million. And for the temperature, they may say it should be between 73 and 78. It really left to the operator how he chooses the band. And second scenario for fault is, space temperature, carbon, CO2 may be okay, but space temperature is outside the range. Why is it so? The third is, we discussed about optimal start, optimal stop. How do you know they are not at fault? They are not faulty. And if they are faulty, what kind of a penalty they impose on the cooling system? So we will address that. The last one is response to real-time pricing. If there is a fault in the lighting when you want to shed the lighting load, then it affects the demand response program. I won't go into detail for that because I already covered enough on the demand response part. Now, let us take a look at temperature and CO2 in the room. If both are within the range, normally we would say, why bother? Nothing to bother. No, that's not true. If you look at the metered energy consumption, and if you compare it with the simulation program with a threshold, maybe you want to say the metered energy consumption should not be more than the simulation program by, say, 8%. If it's high, then I call the metered energy consumption a pseudo fault. I'm introducing a new term called pseudo fault. In other words, the metered energy consumption, nothing wrong with it. It is accurate. But when you compare with a benchmark, it's not accurate. So I call it a pseudo fault. It's something like with your energy consumption for your residential homes. You may find this month's monthly bill is higher than what you thought you had it for last year for the same month. It could be you are opening doors last year more, or you have parties, you are having a lot of lights going on. So in that case, the metered energy consumption for you is accurate, but it's a pseudo fault, and you have to diagnose what are the causes. Something similar I am doing here. So these are the possible approaches I took as to what can be done, what are the things responsible for increased energy consumption that results in the higher metered energy consumption. So first thing I'm looking at is VAV system with dual duct terminal units, demand control ventilation. I will explain what it is. Cooling coil supply reset, I already talked about it. I will go through that. Control loop analysis and chillers and boilers. Now the first scenario, as I said, both temperature and CO2 for all zones, perimeter zones, interior zones are within the range. Now I am looking at this AFDD for demand control ventilation. Demand control ventilation is nothing but you allow enough ventilation to come in to satisfy the CO2 requirement that it has to stay within a certain parts per million, like 1,000 or 1,200. Now, this is, I have used for all these AFDD rule-based algorithms. There are other types of approaches taken like statistical approach, virtual sensors, model-based, predictive control and all. the approach I took was rule-based. The reason I took rule-based was, if you look at HVAC, there are only finite decision-making you have to do. When I say finite, maybe 50 or 60, you can do it. And rule-based approach is somewhat intuitive. Just like when you have a problem with your HVAC, what do? You said, maybe this happened. If this happened, that should have happened. That's it. That's a rule-based approach. Now, in this case, we are saying, I took a conservative approach. We are saying if the outdoor air ventilation, this way on top, is more than 1.5 times the minimum standard prescribed by ASHRAE, and we are saying the CO2 is well within the range, it's less than 800 parts per million, that's what it is for CO2 there, and we are saying the flow rate, that's the amount of airflow coming into the occupied zones, is greater than 50 but less than 80%, not full flow, because if you look at the CO2 800 parts per million, it shows that there are not as many occupants as we would expect. So I took the maximum flow as less than 80%. In this case, if all those are satisfied, then we are saying the outdoor ventilation is a pseudo fault. That means outdoor ventilation has got a set point controller to maintain the ventilation. So we are saying now, since the ventilation is too high, reduce the set point to lower level to allow less ventilation. If you got a hot outdoor air coming in, if you have got improper ventilation or excess ventilation, that imposes a load on the cooling coil and the chiller, and you face an energy penalty. So that's what I mean by modulating the outdoor air set point downward. Again, ventilation standards are available from ASHRAE. They have the standards for ventilation. I said about CO2, they have the standards on how to calculate ventilation rates to account for CO2 and also any volatile organic compounds, VOC, that may occur because of furnishings and all that. Now, cooling coil supplier said the same story. And we are saying here essentially the rule-based algorithm. If the set point of we are saying that the valve has to be at least 10% open, because if they are all shut, there is no need to do supplier reset because there is no cooling load. So there has to be some cooling load, and you don't want the valve to be 100% open, then you can't increase the temperature of the leaving air because some zones will suffer because they need that cold air. So I am saying here the valve is not 100% open, maybe less than 80%. If that's the case, if the supplier set point is less than what the simulation says should be, then we are saying this is a pseudo fault. You change the set point to higher level. So again, you have got a cooling energy penalty. So you have got a penalty on it. Now, control loop analysis. Now, this you have to know the sampling time. In the control loop, depending upon whether it's a fast loop or a slow reacting loop, fast loops and all, you normally sample every 5 seconds because you have to make sure they reach the set point within a reasonable amount of time. And you time and date the sample and occurrence of step change. When I say step change, for example, if you take a cooling coil, the air coming in, if the outdoor weather conditions change, the mixed air conditions, you may have a step change in the outdoor air temperature or the latent load, or the leaving temperature, you may reset it to a higher level. So you got a step change. And then you have to see what the control loop performance is. How quickly does it start rising? Are there oscillations in it? How much time does it take to come to steady state value? So these are all the things that you have to consider. Now, in this case, because you can't analyze fault detection when the control loop is in action, because it has to maintain control, you can't go and stop things and analyze for faults. So all the data during the control loop analysis is sent to the cloud by the smart building facility management system. And during off-peak, you analyze it and see what to do about it. The operator can set thresholds. He may not want more than 2 oscillations. Now, whenever you have oscillations, imagine a cooling coil. That means the valve opens and closes, opens and closes. So there is a possibility after thousands of such closes, you may have an incipient failure. depending on the manufacturer's data for this repeated on and off cycling, there's a chance that the valve may fail. So you can issue a command to the operator. Maybe it's time to change the valve. You can change it during an occupied period or a weekend or what. So the operator sets the threshold value for faults. And you also have to address the sensor error, missing data, perturbation is noise in the data. How do you address it? You can address it by statistical distribution. That's a separate talk altogether. Now, chillers and boilers. In this case, the monitored values for chilled water reset, condenser water reset, hot water reset, they are not optimal when you compare with simulation results. They are off. So these again are called pseudo faults, and you identify what is the energy penalty or lost energy savings. These again I consider as pseudo faults because the set point controller, nothing wrong with the temperature sensor. Now, so whatever I have done so far is all to the criteria that temperature and CO2 are within range. Only the metered energy consumption exceeds the threshold compared to simulation. Now, all these are given so far trying to explain why your metered energy consumption is high and to take action so that you can bring down the metered energy consumption and save on energy cost savings. So as you can see, fault detection is very important. You save energy. And plus, you also prevent environmental conditions being violated. You also ensure thermal comfort is maintained. Now let us take another interesting scenario. In this case, say CO2 is okay in the zones, but temperature is not okay. What do? How do you diagnose where the fault is? Let's see. Now, if you take a zone, all the interior zones, you are saying CO2 is within range. You are saying zone temperature is outside the range. You are talking about cooling coil discharge temperature. We are saying it is at the supplier reset as dictated by the simulation programs. Now, the fact that CO2 is normal, it indicates we have satisfied ventilation requirements. Now, if the interior zones, we are now talking about interior zones, is less than 80% of the full flow, it should really be 100%. If the temperature is not satisfied, you want to make sure whether the flow coming into the room or the occupied zone, is it at 100% or not? If it is not 100%, there is a controller which keeps repeatedly changing the set point at different flow rates. If it's a full load, it should really set it to 100%. So that means the fault is with the DDC control not setting the maximum flow set point. Or I mentioned about the variable air volume box with damper blade which modulates the hot and cold air, and during the cooling season it should completely open to the cold air. Maybe the damper blade is stuck. If it is stuck, you don't have enough air coming through. Or the flow rate could be at maximum flow rate, but yet the temperature is not satisfied. In this case, the variable volume box itself is undersized. So when it is undersized, you don't get the maximum flow. So the fault detection identifies 3 scenarios for the operator to look at. Look at DDC controller for maximum flow set point. Look at whether the damper is stuck. Look at whether the VAB box is undersized so that you can take action. Now, decision of optimization program. This is concerning the optimal stop I explained to you. If the optimal stop does not stop properly ahead of time, say if the room temperature exceeds 78 degrees Fahrenheit, then you know that optimal stop has put a penalty. Maybe it has stopped too close to the optimal situation so that the temperature is increased. So if the temperature increases, you put a penalty on the optimal stop program. If you look at the outdoor air temperature, and weather stations give you data sometimes in 3-degree intervals. And then you can calculate the bin interval of that temperature, and for the entire cooling season, accumulate so many hours of discomfort occurred for that outdoor temperature and start accumulating for every outdoor air temperature that occurs at that time. So that's the penalty. And if the opposite is true, suppose before when you have the optimal stop time, if the temperature is satisfied, then you know that you have a chiller savings penalty. Now this I won't go through, we've already gone through demand response. Please read the conclusion about this AFDD. Have you read this? Now here comes my microphone. Can you hear me now? Now here is, I did experiments because my topic was, are they smarter than Alexa? So I said, for my own curiosity, I bought this in October. And I said, how can I prove it? Whether it's smart or not, whether it's smarter than the smart building facility management system. So this is the Echo Plus I've got, and this has got a smart home hub, and this one cost about $149. And this is the setup I did. My focus was on energy consumption more than getting recipes for cooking or anything. I mean, I did try sports, I did try music, very good, pretty good. I did try Newsflash, I did try audiobook. So I did all that to make sure that how smart it is as far as information on demand. So now if you look at this one, this is the smart outlet. This is a Samsung smart outlet I got, thinking that it will be compatible with my Echo Plus. Unfortunately, it was not. Though Amazon said it was, I had to buy this home smart hub, Samsung smart hub I had to buy. But then Amazon nice enough to give me the refund for the smart outlet. So this is connected to my TV, and this smart outlet is connected to Alexa Echo Plus itself. And this is my internet modem, and this is my router. Now I wanted to see how accurate this smart outlet samples every 5 seconds and gives the power consumption in watts. And you can store data in the Samsung Smart app. App is there for that. Up to 1 week of data you can store. Now here I had a 75-watt bulb, regular bulb, not energy efficient. And I took on 2 occasions. Once it was 75.1 watts, and the other time it was 74.9. So I thought for my purposes it's accurate enough. Now this is the other reading I took of the incandescent bulb. This is Alexa when you didn't have any conversation, no interactions. It came to 2.3 watts. And here, this is on. If you tap on it, it will turn off the device. From anywhere, you can turn it off from anywhere you are. Now this Samsung Smart Hub can connect up to 100 devices. And its range is 150 feet, 100 to 150 feet. So now I got Samsung Smart Hub. In a way, I got Alexa Smart Hub. I can now connect Amazon devices, compatible devices, and Samsung smart devices. I have connected so far to laptop, to my floor lamps, and my TV. Now this is the screenshot in my iPhone of the Samsung smartphone. I told you on the right side you got the time at which the sample was taken by the smart outlet, and you can see it's Echo Plus, and below that, I don't know whether you can read it, it's number of watts. Can you see it? It indicates the watts. So you can see from the watts, you can calculate energy consumption. This is again for the newsfeed mode. In the newsfeed mode, it was not continuous. Suppose it gives BBC News, there is a lot of pause, then you get the New York Times, and there again a lot of pause. So when you calculate the energy, it's like going a little bit up and down. So that's why you will find the total average watts of this is slightly lower than the audio book where it is continuous. This is the music mode watts. I asked it to play Christmas music, and actually it played rock and roll Christmas music. And so again, there was pause because between each track it paused, then came back to the next one. You can see the date on which I just did quite recently. This is in the audio book mode. This was probably the highest watts. Again, as I said, the reader was doing non-stop reading and high pitch and low pitch and so. And this I had set up in the smart phone app to let me know. I had set up two levels, upper limit and lower limit. If the smart outlet indicates a wattage below my lower limit to let me know. In this case, I put 1 watt as my lower limit, and upper limit, I think I kept 3 or so. So automatically I got a text message because you have all the two options. I turn my TV sometimes with my remote as usual, turn it on and turn it off, or I used Alexa or my Alexa app, or I could use the app I showed you, the Samsung app, to turn the TV on or off. I use Alexa because otherwise I don't want to take out my phone all the time. I just Alexa, turn on TV, turn off TV. Now, when you turn off TV through the outlet, it disengages the power to the TV. In other words, standby power is 0. So that's what indicates here. The TV power is 0. Whereas when you have through the remote, there is standby power. And I couldn't get it through the smart outlet. I couldn't get the measurement. I called Samsung tech support group and gave them my model number. And they said in the standby mode, my TV, a 40-inch TV, consumes 26 watts. So I will show you energy analysis, how I come up with payback, annual energy consumption and all that. Now here is the TV mode versus watts. The top one is TV watts, remotes off. As I said again, using the remote to turn off the TV without unplugging from the wall or any outlet. That consumes 26 watts according to Samsung. When you do with the Alexa, it is 0 watts using the smart outlet. And when the TV is on with the outlet, you get 68 watts as far as my measurement goes. If you have bigger TVs and all, you will have obviously more wattage consumption. Now here is the laptop mode versus watts. When my Toshiba 15-inch laptop was charging, it was consuming 4.2 watts. And it was in the hibernate mode, it was about 6.2. When I put it to sleep, it was 10 watts. And when it was off with the outlet, it was completely 0. But I couldn't get standby power because I thought of calling Toshiba. Mine is an older model, and they charge per incident. So I thought I'll be paying more than I'll be saving. So I didn't bother to call them. Whereas Samsung was nice enough, they put the tech support group and they gave me all the details. But I would think maybe you are consuming about 4 watts in the standby power. Because the sleep mode is 10, hibernate is 6, and I would say it's 4 or 5 watts maybe. I don't know. I just guess. So you can see here, I will come back to the final report. If you look at, if somebody in your kids in your house or somebody is having computer, they may work on a computer for 6 hours and leave the computer on throughout the day. So I took that as a condition, working for 6 hours a day and not shutting it off or putting it on sleep. If you don't put on sleep, what is the energy savings like? What is the payback like? Same thing I did for TV also. So anyway, This is the mode and the watts for different types of operation of. When the Toshiba was on, it was consuming about 40 watts. So you get a saving of 30 watts. When you put to sleep, you get 30. Now this is the Alexa mode for different modes. As you can see, when you turn it off with a smart outlet, is 0. When it is in the audio book, I can't read from here, I think it's about 3.9. The music mode is about 3.4. The newsfeed mode is 3 watts. And the quiet mode, when you don't do anything with her, it is 2.3. And this is the table of energy analysis with the Alexa smart outlet I did. On the left side top is the TV analysis. I went through all that in the table I showed you. The annual kilowatt hour savings in the TV mode is mainly the standby power savings. Using TV 3 hours a day. I don't know whether you guys use more than that. I use 3 hours. So based on that, it consumes about 199 kilowatt hours per year. And at 30 cents a kilowatt hour, I use the MG&D, added the distribution charges and energy charges. It comes to about 13 cents a kilowatt hour. Based on that, your cost savings are about $26, and the smart outlet costs about $34. So you have a payback of 1 year. You may ask me, why don't you include the cost of the smart hub as well? That costs $50. But then if you look at the smart hub, that serves up to 100 devices. It's not fair to add it to the cost of the outlet. Even if you add it, the payback is around 2 years. So I don't think anybody throws away the TV every 2 years. At least they own it for 3-4 years, I would think. So you will have an immediate payback with the TV. And at the left side bottom is the Toshiba laptop. Again, I assumed, as I said, 6 hours of use every day, and the remaining hours, you just keep it on without putting to sleep. So essentially, sleep hours are 30 watts sleep hour savings, and you calculate for 18 hours not on sleep, and you get kilowatt hour savings per year, about 200 kilowatt hour savings, and the annual laptop cost savings is about 26, the payback is 1 year. And the right side is the Alexa mode, which I described, how many watts it consumes. And the Alexa, I put it as using 3 hours a day. Alexa, I don't know whether you guys use more than that. I get tired of her if I use too long. So anyway, I use 3 hours. So based on that, Alexa kilowatt hours per year is about 21 kilowatt hours. And the amount of cost you pay to use that is about $3. You use for the Alexa Echo Plus, you use about $3 to run it. Now the interesting thing is, so far Amazon has sold Echo products, Alexa-based Echo products, about 10 million. This is more than a year-old data. Now if you take 10 million, so far it's consuming 210 million to 211 million kilowatt hours per year. Now imagine about Google having Google Home and all that. They all add up. So anyway, this is the thing. Now conclusion, please read the conclusion here. I'm saying Alexa is smart for on-demand information. Alexa is smart for compatible paired devices. Alexa is only as smart as the paired devices. Suppose you connect to 3 types of thermostats, smart thermostats. Not all smart thermostats are alike. If you take Nest, probably it is the most intelligent. Alexa will do everything Nest does. Suppose you pair it with another type of thermostat, which is again a Wi-Fi smart, but it doesn't have all the functions. Alexa can do nothing more than what that thermostat can do. You can tell it, change set point, set it up for parties, set it up for this, you can do that. But Alexa, that's why it says only as smart as the end devices, pair devices. Alexa is smarter than the smart building facility management system in terms of energy consumption analysis, which I had to do manually, as you saw. I had to do the whole thing manually. with Alexa paid, whereas the smart building facility management system I indicated to you is all automatic, except for operator intervention when there is a fault that he has to fix it, which doesn't have a resilience and self-healing capability. Now, there is hope. I feel if the next generation Alexa, their potential exists for Alexa to be as smart as the smart building facility management system, provided we take about 2 to 3 steps ahead. We need to have a smart home energy management system. Now, if you have a smart home energy management system, if you collect all the data, and if Amazon Cloud, AWS service is smart enough, and if they can work with the home automation energy management system company so that you dump all the data into the Amazon Cloud, and then make Alexa more smart to capture the data in terms of energy consumption, savings. And so when you ask Alexa, what is my savings with my air conditioner? Then it can spit it out for you. It's more useful. Then I will say it's as smart as the smart building facility management system. So this completes my talk. And before I proceed further, I would like to introduce a guest speaker, and he's going to critique my presentation, and then I will issue a rebuttal, and then I will open up for Q&A with the audience. Before that, I have to charge myself.
Oh, thanks, Raj.
Before I introduce the next speaker, please join me in welcoming the next speaker. Take it away, Howard. Hello again, everyone. This is Howard Cosell talking to you from Madison, Wisconsin. This is ABC special edition of Wednesday Night at the Lab. This show is brought to you by Pepsi. Now you see it, now you don't. By GM, baseball, apple pie, and Chevrolet. By Imodium, don't leave home without it. Accompanying me this evening are the Gipper and Dandy Don Meredith of Chugga-Lugga Lipton fame. Frank, before we get into Raj's presentation, did you see Ali in the audience? Who can forget the thrill in Manila between Ali and Smoking Joe Frazier? We saw in the 9th round Ali bleeding profusely from his left eye. Then came his trainer, Angelo Dundee, whispering to Ali to sting like a bee. Then came the 10th round. Ali connected with a powerful left hook that floored Smoking Joe Frazier. Now coming back to Raj's presentation. Raj, I didn't finish the Howard Cosell. Raj made a dumbbell of a presentation. I think he gets an incomplete grade, Frank, since he didn't address many of the issues that I have in mind. Question 1, who sets the real-time pricing, Frank? Who uses Raj's demand response program? What about demand response program for residential buildings? Why didn't Raj use AFDD during the commissioning process itself? How much savings do you get with the AFDD? Why didn't Raj address the issue of 210 million kilowatt of hours of energy with the Alexa Echo products? This is Howard Cosell saying so long and good night from Madison, Wisconsin. Here is my response to Howard's comments. I leave it to the audience as to whether it was a dumbbell of a presentation and what grade should I get for my presentation. Who is responsible for providing real-time pricing? MISO, MISCO, Mid-Continent Independent Service Operator. This is a consortium of about, I think, 15 utilities in the Midwest and South, including Arkansas and Louisiana, and some utilities to the west, and Manitoba in Canada. Has anybody used Raj's demand response strategy? The paper I presented in Denmark last year was downloaded close to 600 times by scientists and engineers from over 65 countries. So I have a strong feeling they must have implemented it as a function of outdoor air temperature, the control strategies in response to real-time pricing, though they might not have gone through the route of commissioning. And with the result that I would think if they indeed did like that, it will result in a suboptimal strategy in terms of energy cost savings. What about demand response for residential buildings? This is a good question. I appreciate that Howard asked. MG&E is doing a pilot study with 500 customers for MG&E to directly control the set point of smart thermostats so that they can control the air conditioning load. And this is a pilot study that's still going on. Why didn't Raj use automatic fault detection and diagnosis during the commissioning process itself? During the commissioning process, with the correctness of operation of equipment and controls being evaluated for the entire building, potential exists for hundreds of faults to occur simultaneously, making the use of AFDD no better than manual checkup. Remember, in commissioning, everything is in a chaotic situation. You are going to test for performance and functionality. How much energy savings do you get with AFDD? According to DOE report, you can get about 15% energy savings, very conservative estimate, with fault detection and diagnosis in existing buildings. Has anybody used Raj's AFDD method? A leading building automation systems company has used it, may not be entirely, but maybe portions of it, after I gave them a presentation to them, because mine was a public domain paper, and they asked for it, so I gave a presentation. Raj didn't say how he proposes to handle the more than 200 million kilowatt of energy consumption by the Alexa-based Echo products. I thought I should mention this to you, but not in great detail. I have given ideas to 2 UW departments on how to take cities like Middleton, cities like Fitchburg, completely off the grid. And I cannot go further details because the prototype is yet to be built. So these are my answers to Howard's questions. And now I open up question and answer to the audience. Yes, please.
When a big building implements these kind of strategies and moves their load around, do they need to give that information back to the utilities so that they can refine their plan too?
So far, the one I showed you, nothing is there presently. It's all my vision and my methodology how to do it. Even if you remember one of the flow charts I had, utilities had a feedback about demand response program, whether it was successful or not, based on the smart meter they had, and back and forth information between the smart building facility management system and the electric utility. So they can send back in theory, but it is not happening yet.
In terms of temperature or CO2 that you gave examples of, my guess there would be an inertia kind of issue involved with temperature. It takes time for the temperature to go out of sync, and it'll take time and energy to bring it back in, or something like this. How do you take into account the temperature inertia or the CO2 inertia that sits in the building before you start making corrections to it? That is, if they're out of whack, how much of an energy push do you use in order to bring it back in compliance, or do you do it slowly at a gradual pace? How do you measure the inertia side?
Every control loop, when you study the performance, there is a response time. You know by modeling, if it is out of whack, say it is 79 degrees instead of 78, for the 1 degree, you know what the outdoor conditions are, what the indoor conditions are, and what is the response time and the delay time and lag that occurs all the way from one end to the other, and then you make the control loop respond quicker, so that there will be certain lag time. It won't be instantaneous. Suppose it goes to 79 or 80, it won't immediately react. I mean, the valve damper is open to allow more cold air to come in, but there'll be some reaction time to the variable speed drive. That's the one which furnishes the additional higher flow rate. There is a slight lag in it. So for that period, you will have certain discomfort minutes. It won't be hours, it will be minutes. And then it will settle down. Did I answer your question? Any questions, please? You had a question? Yes.
In your Alexis example, do the smart switches draw power when they're waiting to be commanded? You know, that you've turned off your TV through your smart switch, but doesn't your smart switch have to be on all the time to wait for a command to turn the TV back on?
No, it doesn't have to be on.
But I mean, isn't there going to be a power draw in the smart switch in order to be able to receive the signal to turn back on again? Similar to the power draw in a remote control on a TV?
I didn't investigate. I didn't investigate the smart outlet as such, other than noted down the what.
There's some power drain in that smart outlet all the time, waiting to be controlled, just like in the TV.
I cannot tell you definitely the answer for it because I haven't done the investigation. Maybe I can come back to you at the next Wednesday at the lab. I will call smart Samsung tech support because they are the people who sold me the smart outlet. I will ask them whether there is any standby power that goes with the smart outlet. That may answer your question.
Raj, your fellow engineer is back here.
Yes, please.
So when you were issued your patent in 1978 with Johnson Controls for thermal storage, did you think it would take this long for them to implement, to use your thermal storage?
That was actually, that thermal storage was an interesting concept. That was based on an organic compound for ethylene carbonate. That was during the time when you had a lot of oil, and I was looking at byproducts of oil-based product derived from ethylene glycol.
So ethylene carbonate what Han Solo was frozen in?
Pardon? That had a melting point, I think, of about it's more than 30 years since I did that, 35 years or so. So that had, I think, melting point of 95 degrees, and it had a latent heat of about 66 BTU per pound.
How does that compare to
water? Water, latent heat of fusion at 32.
So twice?
Yeah. And then that was quite an interesting thing because that was a supercooling fluid. So in other words, once you heat it, when you come down, it doesn't freeze. It keeps supercooling. So I devised a method to prevent the supercooling, so to freeze it back. So what I had was put these PCMs, phase change materials, in the air handling system itself, And during the heating season, you can use it as a preheat coil. And that's what I did. Again, I'm sorry, I can't give you more details as I did about 35 years ago.
What kind of Any other questions?
Yes, please.
There's a lot of work being done, including some here in Madison, on sensors paired with microprocessors running algorithms that detect HVAC equipment and air handlers, motors, valves, and so forth to detect when they're approaching a point of failure, as opposed to preventive maintenance when you're hoping you might get there in time or after the fact. In terms of the AFDD, I'm wondering if those kinds of things are likely to complement the concepts you had here in AFDD or even replace AFDD.
See, the things you are talking, it comes under the domain of Internet of Things.
Yep.
Now, in the case of Internet of Things, in fact, that is an ongoing thing of mine. For example, if you take a chiller, right now we have sensors which do only one measurement, like it measures temperature or it measures this, nothing else. Now, with the Internet of Things, you could have a sensor in the chiller that can possibly calculate what's the vibration of the chiller is. It can possibly calculate what is the flow rate. Everything is self-contained in one. And it can talk to other sensors also. So same thing with fault mode also. It can detect, instead of, it can, if any converses with other sensors, Internet of Things smart sensors, it can converse with each other and then find out whether there is a fault or not. So it is really a higher level of computation, and mine doesn't do that. What I have proposed today doesn't do that. That is taking one step higher.
Any other questions? If not, thank you very much.